A quick review of the elementary function properties. Our basic three elementary functions: addition, multiplication, exponentiation, which governs both powers and exponents. Addition, adding two numbers, you can add in any order, and you can add zero. Add zero is two properties for me. Adding zero doesn't change. Adding the negative gets you zero. Multiply two numbers. Multiply in any order. Multiply by 1, which is really two things for me. Multiplying by 1 doesn't change. Multiply by your reciprocal to get 1. X to the y. Order matters, and so you give names to the arguments, the base and the power, or the exponent. Either one is used. There's only two properties that connect exponentiation to the previous addition and multiplication: add powers, multiply bases. Multiply powers, power the power. And for backwards compatibility, we define these operations. Connecting addition and multiplication, there's a distributive law. This is your bridge between the two operations. It's a bridge between a multiplication and exponentiation from the two basic properties. The powers distribute over multiplication. Once we have sine and cosine, which are geometrically defined, then we have all the elementary functions. We'll use the 17th century definition for trigonometry, which are points on the unit circle. Every point on the unit circle has an xy coordinate that satisfies the equation x squared plus y squared is 1. To make it trigonometric, we are going to think of walking back. The length of that arc is my input. The output then is the coordinates, sine and cosine. Input an arc length, a piece of string length. Output coordinates. And then we make the subtended angle the radian measure. If we restrict our attention to the first quadrant, then we have the familiar triangle definitions. Theta is the arc length. I'll draw my triangle in, measure my coordinates, sine theta. Cosine theta. Extract that triangle. Use the rulers to measure the lengths. This triangle is completely determined because I have a unit hypotenuse and two angles. Three pieces of information given, so it is then similar to all other right triangles. And then we get our familiar SOHCAHTOA things: sine over 1, opposite of hypotenuse, cosine over 1, adjacent over hypotenuse, etc. One of the more surprising things is that there's not that many trig identities. Here's how you generate all of them. Take a chord on a circle and rotate it. Put on a coordinate system. The arcs give names to. Traveling A units, traveling B units. So then that arc is B minus A units. Use the definition of sine and cosine to extract the coordinates of the point. So this point has coordinates cosine B minus A, sine B minus A. Similarly, these 2 points have the same sine cosine definitions. And this point is fixed. The length is the same for both chords, so their squares are the same. Pythagorean theorem to get the distance. Pythagorean theorem to get the distance. Use the sine squared plus cosine squared is 1 Pythagorean theorem. And grind out a little algebra, and we end up with these terms remaining. The addition identity for cosine. So there's only 3 trig identities: the Pythagorean theorem and the chord shifting identity, the addition identity. The identity for sine is similarly found. Just move it to the north pole instead of the equator point, and it's the same construction. For the negatives, it just toggles the sign. And then the special case, if A and B are both equal to theta, then we have our double angle identities, which are just a special case of the addition identities. And that's it. That's all the trig identities there are.